Hello everyone, my name is Tirthak. I'm going to be talking about UREQA, which is a technique for leveraging operation-aware error information in order to optimize circuit mapping in NISQ-Era quantum computers. So before we get into the problem statement and our solution for the problem, I'd like to provide a little bit of background about quantum computing. So as we all know, quantum computing is coming in a big way. Different vendors are investing a lot of different R&D efforts into different kinds of quantum computing technologies. The most promising of these technologies so far is the superconducting qubit technology, mostly because it's scalable and it has faster computational power. So the vendors that are putting their might behind superconducting qubit include IBM, Google, and Rigetti. As we can see here, these are the refrigeration units which store the superconducting qubit chips, because they need to be operated at extremely low temperatures. So uses of quantum computing include quantum cryptography, which is the most famous one, but these uses also extend to simulation of molecules, atoms, or any other particles which are inherently quantum mechanical in nature. The problems also include quantum communication and even optimization problems in the fields of finance, transportation, or cloud computing. Quantum computing can be extremely efficient at solving optimization problems. In fact, recently, using their 53-qubit Sycamore chip, Google demonstrated that it can solve a problem within just few seconds, a problem which would take days to solve on even the largest of classical supercomputers. Next, I'll introduce some mathematical theory behind quantum computing. So we know that a classical bit has two states, a 0 and a 1. Here the 0 and 1 are represented using a bracket notation. The 0 is shown as a 1, 0 vector and the 1 is shown as a 0, 1 vector. But a quantum bit or qubit can exist in a superposition of both of these basis states. So a qubit can be represented using state psi, which is a linear combination of alpha 0 plus beta 1, and alpha and beta here are complex numbers. And the norm of alpha squared plus the norm of beta squared is equal to 1. And the reason for this is because upon measurement, the qubit superposition collapses, and the qubit can be found in one of the two basis states using the corresponding probability of their coefficients. So for example, state 0 would be found with probability norm of alpha squared, and state 1 would be found with probability norm of beta squared. A qubit superposition can be represented on a unit sphere known as a Bloch sphere, which helps with the visualization of a single qubit. So in the sphere shown here, the north pole or the positive z-axis is the 0 state, and the south pole or the negative z-axis is the 1 state, and the x and y plane show the phase of the qubit. So qubit superposition can be represented as a vector pointing anywhere on the sphere. So for example, if the vector is pointing straight up, then that means that the qubit is in state 0 only, and when it is measured, it will be measured in state 0 with probability 1. So now we can actually show how we can apply a desired superposition to a given qubit by applying quantum operations, which can be represented as rotations on these Bloch spheres. Now let's look at an example of how these rotations can be applied using the three Bloch spheres that are shown here. So in the first Bloch sphere, we see that the qubit is initially in the ground state, which means that the vector is pointing straight up towards the 0 state. Then we apply what is known as the H gate or the Hadamard gate. The Hadamard gate puts the qubit in an equal superposition of the 0 and the 1 states. So if we see that after applying this gate, the vector is pointing towards the positive x-axis, which means that it's halfway between 0 and 1, and when it's measured, there's equal probability of measuring both 0 and 1 states. And the fact that it's pointing towards the positive x-axis means that it has a positive phase. Then we apply an RZ gate, which is the rotation gate about the z-axis, and we'll apply a rotation of 90 degrees. And we see that that makes the vector points towards the negative x-axis. And even though now the probability of measuring 0 or 1 is still the same, which is equal for both the states, the qubit now has a negative phase. Next, we'll look at multi-qubit systems. The simplest of a multi-qubit system is obviously a 2-qubit system. In a 2-qubit system, there are 4 states, 0, 0, 0, 1, 1, 0, and 1, 1, as are shown in the top row. And you can imagine how this notation can be extended to n qubits with 2 to the n states. So imagine that these two qubits initially are not entangled with each other, and I'll explain what entangled means in the next slide. So qubit naught is in state psi naught, which has the shown superposition, and qubit 1 is in state psi 1, which has the shown superposition. And we take a tensor product of both of these qubit states to get our psi naught psi 1 state, which is the representative of this 2-qubit system. So the psi naught psi 1 state is a superposition of the 4 2-qubit states, each with the shown coefficients. So while the multi-qubit systems where the qubits are not entangled can be represented as tensor products of the individual states of the qubits, once the qubits are entangled, this can no longer be done. So 2 qubits can be entangled using 2-qubit gate operations. As an example here, we have shown the Bell state, where the state psi naught psi 1 has half probability of measuring state 0, 0 and half probability of measuring 1, 1. But the probability of measuring state 0, 1 and 1, 0 is 0 because their coefficients are 0. And we see that this superposition cannot be represented as the tensor product of their individual states because the equality shown here cannot be satisfied. Now these 2-qubit gates and 2-qubit entanglement operations are very common in quantum computing algorithms. For example, there are 2-qubit gates known as controlled Hadamard or CH, controlled rotation about the x-axis, controlled rotation about the y-axis, and controlled rotation about the z-axis in the block sphere. Here, one qubit acts as the control qubit and the other qubit acts as the target qubit. So the state of the target qubit is changed based on the superposition of the controlled qubit. So for example, if we have the controlled Hadamard gate, if the control qubit has state 1, then the Hadamard gate is applied to the target qubit. Otherwise, the Hadamard gate is not applied. And all quantum algorithms or quantum circuits can be broken down into these 1 or 2 qubit basis states. Next, we look at how a superconducting qubit quantum computer is actually constructed. So in the demonstrative figure on the top, we see that there are 2 qubits, qubit 0 and 1, each represented using a gray block. And when we zoom into qubit 1, we see that it's constructed out of a capacitor and a superconducting Josephson junction. And these two elements behave like a nonlinear LC oscillator, which can serve as a quantum particle if the circuit is tuned just correctly and at low temperatures. We see that the 2 qubits have readout and control resonators which supply a microwave tone at the frequency of the qubit in order to apply a desired superposition. And the 2 qubits are also connected with each other using the coupling resonator, and this resonator can apply microwave tones which can entangle these 2 qubits. At the bottom we see an actual 5-qubit IBM chip, and again we see that the squares are the 5 qubits, and some of the qubits are connected with each other using coupling buses, and all of them can be controlled using the readout or control resonators. So these small-scale superconducting qubit quantum computers are known as NISQ computers. NISQ stands for Noisy Intermediate Scale Quantum Computers, and they're used for developing the technology behind quantum computing and showing the usability and effectiveness of quantum computers on different quantum algorithms. But the noisy in NISQ refers to the fact that these devices can be highly erroneous. For example, there can be errors in applying the microwave pulses for the control and coupling resonators, which can cause 1 and 2 qubit gate errors. There can also be errors in reading out the state of the qubit, and the qubit state can be misclassified, and these can cause readout errors. In fact, there are also errors related to the qubit's natural decay to its ground state, known as its T1 coherence time, and also its phase damping due to environmental factors, known as the T2 coherence time. In the next few slides, we'll look at how quantum algorithms are executed on NISQ devices and how their errors can be reduced. So in the figure shown here, we see that quantum computing is actually a hybrid approach between a classical computer and a quantum computer. First, the quantum algorithm is coded up on a classical computer, and it's sent to the quantum device for execution. So for your example, here we have the quantum phase estimation circuit on 3 qubits. The horizontal lines here indicate the operations that are applied to individual qubits as time progresses, and the square blocks show the operations that are being applied. So for example, for qubit 0, first we have the H gate, or the Hadamard operation, that is applied. And then it has the controlled RZ gate, where the qubit 0 serves as the control qubit, and qubit 1 serves as the target qubit. So if the qubit 0 state is 1, then RZ gate is applied to the 1 qubit. And then we see that again a Hadamard gate is applied, and lastly the qubit state is measured, which is shown using the M gate. And once all of these states are measured, the results are sent over to the classical computer for analysis. A major question when executing a quantum algorithm is how to actually map the algorithm onto a quantum computer. So as we saw, quantum computers can have multiple qubits, but they can also have different layouts. For example, here we have the Yorktown and Vigo quantum computers from the IBM cloud. And while both of these systems have 5 qubits as shown by the circles, the arrows between them, which show the coupling resonators, vary in numbers. So for example, Yorktown has 6 coupling buses while Vigo only has 4. So if 2 qubits need to be entangled and there is no coupling bus connecting them, then they need to be swapped in a way that the two come right next to each other and that there is a coupling bus between them. So as you can imagine, a single quantum algorithm can be mapped in different ways on the same computer, and each mapping here is referred to as a circuit map. So for example, here when we look at the Vigo layout, if our algorithm is 3 qubits, then it can be mapped using circuit map A, which is shown on the left, or circuit map B, which is shown on the right. The selection of circuit map is an important problem because depending on the chosen circuit map, the quantum algorithm can experience different degrees of error. So here we have the Vigo layout again, and we have circuit map A on the left and circuit map B on the right for a 3-qubit algorithm, and our goal is to decide which one of these two is better. So with circuit map A, we see that the 3-qubit that it executes on have error rates of 1%, 2%, and 3% for the 1-qubit operations, and the coupling resonators have both error rates of 3%. While for circuit map B, we see that the qubits have error rates of 2%, 4%, and 5% for the 1-qubit gate operations, and an average error rate of 4% and 5% for the links between them. So clearly in this case, we would want to choose circuit map A over circuit map B because the individual components in circuit map A have lower error rates. So if we choose circuit map A, then we would expect that our final output would also have a lower error. So in the figures at the bottom over here, we show the correct probabilities for our final output. So here state 1, 0 and 1, 1 have higher probabilities than state 0, 0 and 0, 1 for our expected correct output. And when we run the algorithm with using circuit map A, we see the observed probabilities in the sky blue bars, and we see that these are pretty close to the correct probabilities that we expect. But when we run the same algorithm using circuit map B, we see the observed probabilities that we get are the green bars, and these bars can be far off from the correct probabilities. So it is in our interest to choose circuit map A to execute our algorithm because it has lower error rates for the individual components, which results in a lower error rate for the final output. Next, we look at how we define the error rate of the final output. So here the correct probabilities are shown in blue and the observed probabilities are shown in green. And we have a 2-qubit 4-state system, state 0, 0, 0, 1, 1, 0, and 1, 1. And their errors are calculated as shown here. So E00 error is the difference between the first blue bar and the first green bar, and E01, 10, and 11 are similarly calculated for all the bars. So the overall output error is the sum of all of these errors divided by 2. Next, we'll look at the impact of circuit map selection using a real quantum algorithm. As we saw earlier, the quantum phase estimation circuit runs on 3 qubits and has 8 program output states, with correct output probabilities as shown in the figure. So we see that the first 4 states have probability 0, then state 100, 101, and 111 have probability 0.125, and state 110 has probability 0.625. Of course, all of these probabilities add up to 1. So an ideal circuit map, which is run on an error-free quantum computer, should be able to get these probabilities exactly right. First, we execute the QPE algorithm using a low-quality circuit map, which has a high rate of error of the subcomponents. As we see in the results from the yellow bars, the resulting output probability of this circuit map is far off from the correct output probability as shown using the hatched bars. In fact, even the states which have 0 output probability have occurrences of output probability using the low quality circuit map. And we see that the overall output error is 28%. Next, we look at the QPE algorithm when it is executed using the optimal circuit map. This is a circuit map which has the highest success rate or equivalently the lowest error rate. The success rate of a circuit map can be estimated using the success rates of its individual components. As shown in the formula here, the GIs are the success rates of the gates which are used in the circuit, and the MJs are the success rates of the readout operations which are performed at the end of the circuit. And if we maximize this product, we get the circuit map which is the optimal one and which has the highest estimate of the success rate. So as we can see in the figure over here, the red bars show the results of the optimal circuit map, and we can see that those are much closer to the correct output than the low quality circuit map's results. In fact, the overall output error is only 6% with the optimal circuit map, while it was 28% with the low quality circuit map. So while we're still not able to achieve the ideal results, we can considerably reduce the error rates. In this case, it's reduced by 22% point, and that can be very helpful for us in order to determine the correct output of the algorithm that we ran. So we can determine the optimal circuit map if we know the success rates of the subcomponents, but it is not always too trivial to know what these success rates would be, especially because they vary from qubit to qubit and they also vary temporally, as we'll see after this. So previous solutions have determined the optimal circuit map by using the error rates of some operations which are performed during the calibration of the machine. And then these error rates are used as a proxy for all operations which are performed on that particular qubit. However, these single per qubit error rates do not distinguish the difference between the error rates among different quantum operations that can be performed on a given qubit. So for example, in the figure on the right over here, we have the orange qubit, which has a 2% 1 qubit error rate, and the red qubit, which has a 5% 1 qubit error rate on average. But if we break it down based on the operations that are performed, then we see on the figure on the right that 4% error rate for the Rx operation, and that there is 2% error rate for the Ry, or the rotation about the y-axis operation. And then similarly for the red qubit, there is 3% error rate for Rx operation and 7% error rate for Ry operation. So if we were choosing the two qubits for our circuit mapping, if we wanted to perform a lot of Rx operations, then we would choose the red qubit. But if we wanted to perform a lot of Ry operations, we would choose the orange qubit. But if this information is not available, then as shown in the figure on the left, we would always choose the orange qubit, because that's the only error rate that is available to us, which is not specific to the operation that is being performed. While the previous slide just showed an example, we found that even on real quantum systems, different operations do have different error rates. If we look at the top row of figures over here, the figure on the left shows the error rate of the Rx operation on 14 qubits on Melbourne, and the figure on the right shows the error rate of the RZ operation on the same 14 qubits. Now, if specifically we look at qubit 5 and 6, we see that qubit 5 has a much higher Rx error rate than qubit 6. So if our circuit has a lot of Rx operations, we would prefer to run it on qubit 6. But if we look at the RZ operations, then we see that qubit 6 has a much higher error rate than qubit 5. So in this case, we would prefer to run the circuit on qubit 6 if it has more RZ error rates. In fact, when we combine the results across 4 different quantum computers and across all of their qubits, then in the bottom figure we see that different operations do have very different error rates. So here we see that, for example, the H operation, which is the Hadamard gate, has an error rate of just 1%, while the Rx operation, which is the rotation about the z-axis on the Bloch sphere, has an average error rate of 5%. We also observed that the error rates exhibit considerable variance for the same qubit and the same operation. So for example, for qubit 1 shown in the figure, the error rate of Rx operation is 10% on median, but the error variance as shown by the range indicators is also considerable. In fact, the operation-specific error rate also varies with the computer. So for example, for the Vigo computer shown on the right, qubit 4 has a very large error variance, while none of the qubits on the Melbourne computer have such a large error variance. So this shows that the error rates not only vary based on the operation, but also the qubit, the computer, and they also vary with time. This means that there is a need to predict the error rates of these specific operations at a given time on a given computer and on a given qubit in order for us to be able to optimize our circuit mapping. Keeping this need for accurate prediction of operation-specific error rates in mind, we propose UREQA. UREQA is a machine learning-based approach to predict error rates of quantum operations. Of course, the end goal of UREQA is to select the best circuit map to execute a quantum algorithm as shown here. But to select the circuit map with the lowest error rate, UREQA first needs to be able to estimate the error rates of the circuit maps for different circuit maps. And to do that, it needs to be able to predict the operation error rates of the subcomponents of these circuit maps. Therefore, the main goal of UREQA is to estimate the error rates of different circuit maps by predicting the error rates of the underlying operations. It is not exactly straightforward to predict the operation error rates. Any rule-based, heuristics-based, or analytical model-based solution would not work in this case because of the instability of the technology. Therefore, UREQA employs a machine learning-based approach which is able to predict these error rates based on the historical information that it has learned during training. So to generate the data for training, UREQA has the training phase, which is a one-time phase where it collects data from running thousands of different microbenchmarks on all of the qubits of different quantum computers. Each microbenchmark consists of a single operation which is run and then measured, and then the error for that operation is generated. Along with these microbenchmarks, UREQA also collects information about qubit coherence times and frequency, which are readily available from the calibration. Then all of this data is fed into the training and optimization model of UREQA, where three separate KNN models are generated for the three different types of errors. One is for the single qubit gate errors, second is for the two qubit gate errors, and the third one is for the readout errors. And then these three models, which are generated at the end of the training phase, can then be used for all future executions of quantum algorithms on these computers. They can be used to predict the error rates of these operations, which can in turn be used to generate the best circuit map, and then this circuit map can be used to execute the quantum algorithm. In terms of the predictive features, UREQA uses the features that are listed in the table over here. For example, for the two qubit gate errors model, UREQA uses the computer ID, the frequency, T1 and T2 coherence types of both the control qubit and the target qubit, as well as the gate type. And similarly, it uses the corresponding features for one qubit gate errors and the readout errors models as well. It does not use features related to the neighboring qubits or other qubits on the same computer, because when we performed a principal component analysis, we found out that just these features account for over 95% of the variance, which meant that the other features which are available on the computer do not contribute majorly towards the predictive power of our models. Next, we look at the evaluation methodology of UREQA. UREQA is evaluated on 4 different quantum computers available on the IBM cloud. These quantum computers have different layouts as shown here, and they also have different number of qubits. In terms of the benchmarks, we look at 6 representative benchmarks, including the Berenstein-Vazirani benchmark, quantum phase estimation, and Simon's algorithm. And UREQA is also evaluated against 2 different techniques. One is the base method, which is where the circuit map is selected just using the assumption that all operations have the same error rate. Then there is the base UREQA method, where the KNN models are developed without any operation-specific information. And then there is the UREQA++ method, where the KNN models for prediction are developed using operation-specific information. When we look at the results from UREQA's evaluation, we see that the operation aware UREQA++ achieves the lowest deviation from the observed error. So if you recall, the goal of UREQA is to be able to predict what this observed error of operations would be. And the deviation refers to the percent point difference between the predicted error and the observed error. In the first plot, we see the deviation of the observed error for 1 qubit gate errors, and we see that for UREQA it is 2.9, but for UREQA++ it's only 1, which is a percent point reduction of 1.9. And this can have a great impact on the overall circuit map, which constitutes of tens of hundreds of these individual operations. And similarly, for 2 qubit gate errors, UREQA++ reduces the deviation from 1.4 percent points to 1 percent point. Next, we see if the predictions made by UREQA++ can actually be used to select better circuit maps. And indeed, based on the results, we see that the circuit maps selected using the error rates predicted by UREQA++ have the lowest error rates across all the quantum algorithms. For example, in the figure, when we look at the QPE, or quantum phase estimation algorithm, we see that the base method, which treats all operations to have the same error, has an error rate of about 25%, while with UREQA++ it's reduced by approximately 15 percent points to just 10%. Please refer to the paper for more results about how UREQA reduces the error rates for different algorithms and different computers. The machine learning models and data of UREQA are open sourced on our group website. Thank you for taking the time to watch this presentation.